Hello, and good morning, good afternoon, and good evening. If you're joining us live or on the replay, I wanted to welcome you to the DDS Foundation seminar series on topics related to the DDS standard. I'm Lynne Canavan. I'm Vice President of Marketing for the DDS Foundation. Today's talk is going to be focused on RTPS, and this is our 11th webinar for the year 2024, which happens to be the 20th anniversary of the DDS standard. So lots of things still happening with DDS and lots of things to come. So let's get started on this. First, just a quick overview of what the agenda is. I'm going to quickly go over what the DDS Foundation is, and then I'm going to turn it over to Justin Wilson to take you through today's topic. So basically, the DDS Foundation is a vendor-neutral collaborative nonprofit that was formed to help grow the DDS usage. So our participants are DDS users of applications that run on DDS, and the vendors and researchers and all the other people in the collaborative community. Our mission is to promote the adoption, interoperability, and success of the DDS family of standards to the wider community. So I wanted to invite you to check out our website. Under resources, you'll see live links to the other webinars that have been held this year and other years, use cases, and more. So again, reach out to us if you have any questions, and hopefully you'll be able to access some of that information and use that in the work that you're doing. So with that, I wanted to turn it over to Justin Wilson, who is the Director of Interoperability for the DDS Foundation. He's also serves as Principal Software Engineer at the OpenDDS Foundation, Unity Foundation. So Justin, over to you.
Thanks, Lynn. So to really ground what we're talking about today, we need to go back in time. So the very first talk in the seminar series was titled DDS, the U.S. Navy and the Need for Distributed Software, and there's a link to it there. I really encourage you, if you have not seen that webinar, to take a moment and go look at it. It's very good and very informative about the history of DDS, which is relevant to our topic today. A brief summary of it is that the U.S. Navy was building distributed systems for their on-ship computing, and they were moving toward commodity hardware. But in terms of software, they wanted software built on a specification so they could be sure about what they were getting, so that they could test it and just have a whole lot of confidence in it. And they had a number of specifications, some of which are listed here, namely that they did not want a single point of failure, they needed fault tolerance, they needed real-time capabilities and things of that nature. So I do want to give a very brief overview of DDS for those of you who may this be the first time you've been introduced to it. DDS defines a high-level container or abstraction called a domain, which is really an application or a set of applications that are put together to accomplish some kind of distributed computing goal. A domain has a number of participants in it. Each participant has publishers and subscribers, and a publisher has a number of data writers, and a subscriber has a number of data readers. The data writers and the data readers coordinate messaging through topics. So a topic can have multiple data writers and multiple data readers, and they use a publish-subscribe model to communicate. So in use, we define a topic using IDL or some other mechanism. It's a strongly typed system. In this case, we have telemetry. It's got a key, which is a string, which indicates perhaps the ID of a satellite, with a message number and a position and velocity. And a data writer can write a value of this, which is called a sample. The key defines an instance. All of the data writers can write, and the data readers, for their part, can have a local cache of the data that has been written by the data writer, and they can read samples from that cache, or they can take samples from the cache, which is destructive. The basic process that would happen is, as the data writers and data readers come online, is that there's a discovery process where they learn of each other's existence. They then match with each other based on a set of QoS parameters that are consistent, and then they start communicating by sending data back and forth. So anyway, back to the initial work from the Navy is that the DDS, or rather, sorry, one step back, is that from this DDS specification, it requires an implementation to adhere to the specification, just like every spec in the world. The spec itself, though, left certain things to the implementation. So for instance, the details of how data makes it from the writer to the reader was left as an implementation detail. Similarly, the discovery process was implementation specific. So the spec delivered an API that allowed you to build applications against that API. And then if you wanted to switch vendors, you could just recompile the code. And that was good. That was useful, and that prevented vendor lock-in. But we needed to go a little bit farther, because what happened was DDS was successful and multiple vendors started implementing it, and users wanted to buy and integrate systems developed by different vendors. So this is a very straightforward idea that you buy a piece of equipment from one vendor that runs a certain DDS from a software vendor. You buy another piece of equipment using a different DDS vendor. You would like to put those together on the same network and have them communicate and work together. And the only way they're going to do that is if they have some kind of interoperable wire protocol where they can successfully exchange information. In addition to that interoperable wire protocol, we need some kind of discovery mechanism so that the writers and the readers can discover each other and know that they need to communicate. So that really motivated the success of the DDS spec, really motivated the creation of another spec, which is called the Real-Time Publish-Subscribe Protocol, DDS Interoperability Wire Protocol, DDSI RTPS specification. It's very long. We typically just shorten it to RTPS, Real-Time Publish-Subscribe. The history of the spec is kind of on the right. RTPS 2.0 came out in April of 2008. And there have been various revisions to it. We're now at RTPS 2.5, which was published in April of 2022. The spec is about 200 pages long. So we're definitely not covering all 200 pages, but my intent for this talk is really to give you a flavor of what's in the spec, so that you can go for further study if you want, or if not, you can have a conversation with people about it and know what everybody is talking about. So the spec itself consists of three major pieces, really. One is the platform independent module. So and I'll get into a discussion of what's covered in the PIM later. The platform specific module, which talks about how the platform independent module is mapped to a UDP IP implementation. And then there's various details about the serialized payload representation. I'm not going to dig into the serialized payload representation. It's a little bit beyond the scope of this talk. So the spec starts by outlining some requirements that it wanted to fulfill. So it says that it, as a specification, was trying to be a trade-off between generality, ease of use, richness of features, performance, memory size and usage, scalability, determinism, and robustness. So you can see a lot of the initial requirements that the Navy had for its system reflected in that. But you also see some other things in terms of just memory size, scalability, richness, and so on, that they wanted something that would accomplish all of the richness that DDS gives you without being, generating excessive overhead and things of that nature. It also admits that there's going to be a strong preference toward unidirectional data exchange. So we have data writer and we have data reader. Data is flowing from data writer to the data reader. In some cases, we might not need any feedback from the data reader. In other cases, we may need feedback if for instance, we need to support some kind of reliable data transfer. So the spec kind of leaned that direction in terms of picking its implementation. And it also admits many-to-many communication. So if there's an efficient way to send one message to a number of recipients, that's desirable. And that's going to lead us to, a mention of multicast later in the talk. DDS is a significant piece of DDS is the quality of service, and there's other talks that have been given in the series about quality of service. We're not going to dig too much into them in this talk, but we needed a protocol that would allow implementations to support all of the different clauses that are available. Some of those have an impact on the wire protocol, others don't. The significant one being reliability, and we'll give an example of that one. And then finally, they wanted infrastructureless discovery. So as people were, again, buying these systems, integrating them together, they didn't want to have to set up a third party to handle the discovery aspect. Instead, they just wanted the peers to conduct discovery among themselves. So they devised a discovery protocol that doesn't require any additional infrastructure to be set up. So to get into some details of the spec, again, there's a platform independent module and a platform specific module. So the PIM is going to define logically how RTPS works. So there's a lot of structures, virtual machines, state machines, messages in a logical format, and then behavior of all of those entities together that describes how RTPS works in a logical fashion. It does not get into how it's mapped to an actual implementation. That's the purpose of the PSM, but the PIM opens the door for one, understanding in general what's happening, but then providing a number of options for how one could implement it in different scenarios. The implementation that is in the spec is one based on UDP IP. So that's the PSM, the platform specific module. And that's largely what I'm going to be talking about in this talk. Other mappings are possible. For example, there's TCP mapping that has been talked about for a while. But the UDP IP one is the main one because it's in the spec, vendors have adopted it, implemented it, and that's the one that most you're going to see in practice most of the time. And the reason I'm not necessarily getting into the PIM so much is because usually when you're looking at a DDS system, you typically see it at the API level where we're talking about readers and writers and participants and so on, and then you see it at the network message level where we're talking about RTPS running on UDP IP. So that intermediate level where the PSM lives is useful for kind of thinking about it, but in for practical reasons, we typically want to relate what's happening at the API level to what's happening at the message level and kind of equate those. So the first choice that they made in terms of the PSM was to deliver or outline, an implementation based on UDP. So that's the user data protocol of the IP suite. By using UDP, they avoid the overhead and non-determinism of TCP. So TCP does have overhead in terms of connection establishment, and then obviously the ACKs and the sliding windows and all of that stuff in terms of how that's managed. That creates non-determinism in the data stream, which real-time applications are sensitive to. So to avoid that, they chose to go with UDP and sidestep a lot of that complexity. By using UDP, it also created the opportunity for using multicast. So you can leverage the network and the equipment in the network to efficiently distribute a message from one writer to multiple readers. And if you have significant fan out, that can be a significant savings in terms of network bandwidth and performance. So moving on from just the fact that this protocol is implemented in UDP, we need to talk a little bit about some basic structures in RTPS. And there's a lot more that could be said about all of these things and a lot more types and things, which I'm not introducing, but these are some really fundamental ones. So the first piece of terminology is really an endpoint. So an endpoint is something that sends and receives messages. In this case, it's a writer. A writer is definitely writing data. and it's a reader. A reader is receiving that data, and there may be additional, communication going on for reliability. But if you're sending and receiving messages, then you are an endpoint in RTPS terminology. Each endpoint has a 16-bit GUID, global unique identifier. The first 12 bytes of that are what's called the GUID prefix, and the last 4 bytes are called the entity ID. So endpoints belonging to the same participant must have the same GUID prefix. How is a GUID prefix made unique? Typically, vendors have what's a vendor ID, which we'll talk a little bit about later. Usually that's incorporated into the GUID somehow, and then from there, the vendor can come up with whatever scheme they want to make their GUIDs unique. There are built-in endpoints, built-in readers and writers for discovery, which are not necessarily influenced by user activity directly. They're influenced indirectly as users create data readers and data writers and things like that. And then there's obviously ones for the user endpoints, which correspond to the data writers and data readers that they create in their application. An endpoint has one or more locators that contain network addresses where it can receive messages. So the main goal of discovery is to communicate not only what data readers and data writers exist, but also where you can send messages to them so that they'll receive that message. And we'll talk briefly about discovery toward the end. So to organize all of this in a perhaps a little bit more graphical fashion, we can imagine we have 2 participants. I've tersely labeled their GUID prefixes 1.2.3 and 1.2.4. There's more bytes than that, but for illustrative purposes, I've used small numbers here. If that participant has a data writer and a data reader, it's going to have a GUID, a full GUID consisting of that prefix 1.2.3, but then an entity ID 1 and 2 in this case. So in this example, I've done 2 participants, each has a data reader and data writer. These could all be serviced by the same kind of RTPS implementation or RTPS instance, in which case they could all share a set of locators. So for instance, that top locator is a unicast for a UDP IP. The second one is a unicast but in this case, it's a local loopback address. Say you wanted to just communicate locally on the same machine. And then the third one is a multicast address where you could reach them by sending a message to them on that multicast group. So again, the locators are typically going to be shared by a number of endpoints, and discovery, the main goal of discovery is to really communicate the existence and the locators for endpoints. Message format. So again, we're talking about a UDP message, and the messages in RTPS have a basic format. It's essentially a header. It's an optional header extension that was introduced in 2.5, RTPS 2.5. And then it's a non-empty sequence of sub-messages. So this sequence idea is interesting because it allows you to combine a number of messages from a number of endpoints, send them all at once to avoid bandwidth, right? So that's an important feature of the protocol that is very common, but nevertheless does have a very, very useful purpose. So what's in a header? So header starts with just RTPS as in a kind of ASCII characters to identify it as an RTPS message. That is followed by a protocol version, which is a major and minor. Again, that would be 2.5 if you're implementing the 2.5 spec. It's then a vendor ID, which is 2 bytes. So every vendor of DDS, every vendor of DDS can submit something to the DDS SIG to get a vendor ID assigned to them. And the vendor IDs are useful in terms of being able to just understand what application is doing what on the network and what system is causing that message to be sent. So it's very useful for debugging purposes. It's very useful for backward compatibility and things of that nature. And then finally, the last piece in the header is the GUID prefix. So that's essentially, since That would be repeated for every one of the submessages in the submessage list. They factored that out into its own byte or its own value in the header, and then it's assumed to apply for all of the submessages. There's ways to change that, but that's done to avoid replicating those 12 bytes just over and over again. The header extension, again, is optional, but it was introduced in 2.5. Contains additional metadata, such as the length of the message, which is can be useful if you suspect that the networking equipment may be truncating things. It's got a timestamp when the message was sent. It's got a checksum, again, to verify that the content has not been altered. And then it's got some additional parameters that can be used by vendors to accomplish various things. From there, the remainder part is the submessages, and this is really where the work of RTPS gets done in terms of moving data from a data writer to a data reader. So the spec breaks down the set of submessages into two groups, really. There's entity submessages, which are really submessages originating from a writer or reader for the purpose of writing and reading. And then there's interpreter submessages, which are really provide additional metadata and create some additional opportunities in the protocol. I'll talk about the interpreter submessages first. So the first one is the header extension, which we've already seen. The second one is an info source submessage, which sets the GUID prefix for the remaining submessages. This would be used if you were building a piece of equipment or a software system that was relaying RTPS messages and needed to read them from one group and forward them for the other, in which case it could introduce its own GUID prefix, but it would say that these submessages are from someone else. You would use that in a relay component. Info destination is used to set the GUID prefix for the destination for certain messages. So some messages, such as an ACNAC, are directed. They go from a reader to a specific writer. So in order to identify which specific writer, infodest can be used to specify the GUID prefix that would be used for that. Info reply provides locators for a response, again, if you're talking about point-to-point communication. Timestamp introduces timestamp of when that data was written. That's used, for instance, if you use write with timestamp, if you're familiar with that from the DDS API. And then there's a pad submessage, which just can be used to enforce alignment in some cases. So that's the interpreter submessages. You do see them in practice, specifically like info timestamp and infodest are used quite extensively. Info source and reply and pad are not used that often. The entity submessage is more interesting. So from the writer perspective, we have a data submessage that actually contains the data for the sample that was written in the API. There's also a heartbeat, which is a way for a data writer to say a couple of things. One, that it's still alive if you're doing liveliness, but it's also a way of saying this is the data that I currently have as through a sequence number range. And I'll talk a little bit more about that later. And then there's gap, which is kind of the antithesis of a heartbeat saying, I don't have this data, please stop asking me for it. On the reader side, there's an ACNAC, which is really the only message that a reader can send. And it's a combination between a positive acknowledgement of I've received this data, and it's also a negative acknowledgement saying I don't have this. So both of those functions are combined in one submessage. I didn't mention the frag messages, but they all correspond to they have a corresponding message. So for instance, data frag is data that has been fragmented. So it's one fragment of that data. Heartbeat means the same idea that I have this fragment. NAC frag is I need to request a fragment from the writer. I won't necessarily get into fragmentation in this talk, but know that RTPS can handle messages that are, for instance, bigger than like your network MTU. So you can set a fragmentation limit, break those messages apart, and then the other side can still receive them. So to give you a flavor of what RTPS is doing, I want to look at how reliability is implemented. So in this diagram, we have a writer on the left, we have a reader on the right, and SN is going to stand for a sequence number. So every message that is sent in terms of data has a sequence number, and then a SNS that stands for sequence number set. So there's a bitmap representation that is defined in the RTPS protocol for representing a set of sequence numbers. It has kind of a base and then a number of bits that are used to indicate the set from that base. So let's start by assuming that the writer, which has a certain writer ID, writes some kind of payload and it's sequence number X. But the network drops this for whatever reason. So the reader never got it. The writer on its part, knowing that this is a reliable reader, has an obligation to communicate with that reader and make sure that it got the data. So either immediately or sometime later, it will send a heartbeat, again, coming from itself. It has its own writer ID, and it may specify the reader ID directly, or it may use a general reader ID, reader unknown, essentially. In either case, it then specifies a low sequence number and a high sequence number for saying, I have data between these ranges. In this particular case, X would be between low and high inclusive, right? So saying I have this data. Let's assume the reader gets that. When the reader gets that, it's allowed to send back an ACNAC, so a positive acknowledgement and a negative acknowledgement. In this case, it would use its reader ID. It's from me. It would specify the actual writer ID of who it wants to communicate with, because it may have multiple writers. And then it also specifies ACK sequence number, meaning it has all of the data below that. Then it has a NAC set, which is I don't have this data. So in this particular case, our X would be in that negative acknowledgement sequence number set. After that, let's assume the writer gets that. The writer would then resend the data, right, which would essentially be a resend, send out the heartbeat again, and then the reader, for its part, upon receiving it, would send an ACNAC now with a new acknowledgement saying, I've received this data, so you don't need to send any more heartbeats for that particular one. It may be missing other data, but in this particular case, it's got that one. So this is the general flow of reliability. If we're talking about a reader that's not reliable, then you just see data messages going from the writer to the reader, because you're assuming that there's going to be another data message and that eventually one's going to get through. Another big feature of DDS is durability, which allows you to replay data that was previously sent. In this particular case, you can think of it almost like the reader wasn't around to hear all of the original data. So it can receive a heartbeat. It can understand what data is available. It can then, using ACNAC, request that data from the writer, and then the writer can send all of the historic data that it needs for durability, and then catch up and continue on. So that's this reliability protocol really helps. It's the way that reliability is implemented in RTPS, and it avoids the non-determinism associated with TCP. Just a few notes. Again, I mentioned these in passing, but a gap submessage indicates that a writer no longer has a set of sequence numbers, and you'd say, well, why does that happen? It's going to be something like it was dropped due to resource limits or some other reason that the writer moved on and said, I don't have it. So just to the way timing works out, the reader may get knowledge that a sequence number exists, but by the time that's communicated to the writer might say, I don't have it anymore. So that's what the gap is there, is to indicate to the reader, I don't have it, move on. And then the frag messages are used when large samples are fragmented, that we've already covered that. So a few more slides here for discovery. So in RTPS discovery, there's two protocols defined. One is simple participant discovery protocol. The other one is simple endpoint discovery protocol. So you go through kind of a three-phase procedure of you do SPDP first, SCDP, and then your data starts to be transferred. So the way SPDP works is we have two built-in endpoints, SPDP built-in participant writer and reader. The writer is going to periodically send a sample that really contains a lot of information, but the basis is it's a list of the other built-in endpoints and a list of locators where you can contact those endpoints, and it sends us via multicast. So every participant needs to join this multicast group. Then the reader reads those samples, gets them, and then kicks off SCDP so that it can discover other things. For the SCDP side, there's publications, writers and readers, subscriptions, writers and readers. There's the topic ones, which are optional. I'm not going to dwell on those. But essentially, you have a writer which writes all of your data writers that are in that participant and the data readers in that participant, and you have readers for corresponding. So in this way, you can announce all of your data writers. You can receive all of your data readers from remotes and learn about those. There's also a participant message writer for liveliness. For whenever you assert liveliness, that's kind of a narrow case that I don't want to dwell on at this point. But then, so over time, RTPS existed, but it became deployed in networks where security was a concern. And now security is obviously a concern everywhere. So the DDS Security spec was ratified and written, and it was really prescribes a number of changes to the RTPS protocol to support it. So the basic changes here, and I won't get into everything, but the basic changes are DDS Security allows encryption and signing at 3 levels. First, you can sign the entire RTPS message, or you can sign individual submessages, or you can sign the payloads of the data in the submessages. And there's various reasons why you would pick one or the other. Typically, it's going to be a trade-off between efficiency and flexibility of what you would like to accomplish. It also adds secure variants of all the SCDP endpoints, so you can securely communicate your publications and subscriptions and create a entirely secure system where nothing is leaked or in the clear. And it also is going to add special endpoints for authentication. Namely, you do a Diffie-Hellman exchange, you exchange your certificates from public key infrastructure, and then you verify your permissions files. Again, I won't get into that, but we have other talks on DDS security. And then there's another endpoint for key exchange, which is really point-to-point exchange of all your cryptographic materials, like the keys that you're using. And these add, this adds additional overhead and steps. So you do SPDP first, you go through authentication, you then do some built-in key exchange for your built-in endpoints, you do SCDP, do key exchange again for your data endpoints, and then you do your data starts to flow. So to summarize, kind of put all these pieces together, RTPS is the interoperable wire protocol for DDS. It's defined in a spec, it's widely implemented. RTPS was designed for the data-centric publish-subscribe model of DDS. So that includes the multiple writers communicating with multiple readers, unidirectional data transfer, real-time requirement, etc. RTPS defines SPDP and SCDP for discovering remote peers and their data writers and data readers so that they can be matched and communication can start. And then finally, RTPS has been extended to support DDS security. It allows you to put various things in secure envelopes, and it also provides additional endpoints for doing authentication and key exchange. So with that, I'll turn it over to Lynn and questions.
Okay, thank you so much, Justin. That was really terrific. Let's see, the first question is coming in is basically asking, or the question is, have most vendors implemented RTPS? So.
Yes. So since RTPS is defined in the spec, that's what most vendors lead with because interoperability is so important. So most DDS implementations that you're going to find have implemented RTPS. And beyond that, there's a interoperability test that is available in GitHub where vendors can submit executables to that test. The test runs, it kind of creates a writer from one vendor and a reader from another vendor, and then ensures that communication took place or didn't take place according to what the test wanted, and produces a matrix to show, this scenario worked, this scenario didn't work. So in that view, we don't know exactly how many people have implemented RTPS, but we do know that a lot of the major vendors of DDS have implemented it, and they are interoperable. There's very few failures in that test matrix, and a lot of that is to do with slight interpretations that will be worked out in subsequent versions of the spec.
Okay, thank you. And just a quick reminder, that interoperability testing portal that that Justin mentioned, that is available. You can find that on the DDS Foundation website, and it'll take you right there. So so please use it. Check it out. We'd love to encourage people to make use of the great work that went into developing that. And the next question is, I guess it refers back to one of your earlier slides, Justin, where you were showing the different iterations of the RTPS spec. Could you go into details in terms of what's up, what's coming, what's next, what's in plan for the spec, what additional functionalities?
Sure. So obviously security, I'll start with two recent things. So obviously security was a very big addition that had an impact on the spec in terms of extending RTPS. Another one is TSN, time-sensitive networks. So there is a spec which defines how DDS can be mapped to a TSN network, and in that spec, it's also going into how the RTPS messages are mapped into that. So that's another use extension of RTPS. I would say for things which are in the works is there's a spec for TCP, and again I kind of talked about the reasons why you don't want to do TCP, but there's still a lot of reasons you do want to do TCP. It kind of handles some of the reliability stuff inherently, right? So you don't get this, you don't get that, you don't engage that reliability protocol in the way that is sometimes non-beneficial. And it also works better in terms of with load balancing and modern cloud computing environments and so on and so forth. So there's good reasons for that. There's also some thoughts on the discovery piece. So since discovery is based on multicast, it only works well in networks where you have multicast. That's typically going to be a local network. A lot of cloud vendors don't support multicast out of the box, so that's a hurdle that you have to get over. So there's been some growing thought about how we could do discovery more in a kind of a service-based way, less peer-to-peer. So that is kind of introducing a third-party system sometime, if you will, but that could be very beneficial. And if that infrastructure component that's needed for discovery is spec-defined, then you get all the benefits of interoperability without creating an integration problem on the other side. So I think those are kind of three areas that RTPS is going. Another one is that, and this I was thinking about this morning actually, that with RTPS being defined the way it is, there's things that participate in a DDS ecosystem that don't necessarily implement DDS as an API. It's just a process which knows how to send and receive RTPS messages. So you see that has happened, and I expect that that'll continue to happen as well.
Okay, great. Thank you. And then the next question that came in is, somebody just wanting to confirm or ask, is RTPS the only protocol for DDS?
RTPS is the only interoperable protocol that's spec-defined. I'll put it that way. So obviously, two vendors could pick another protocol and implement that protocol and be interoperable with each other, but as soon as you get a third vendor, you're going to not be able to communicate anymore. So the fact that it's the spec-defined protocol really means it is the only interoperable protocol at this point that kind of every implementation really needs to support in order to say you're interoperable.
Okay. All right. I don't see any other questions come in, so just want to encourage those that are still listening. Again, if you have other questions, please reach out to us. Those of us at the DDS Foundation, please visit our website. And I wanted to extend a huge thank you to Justin for a really informative and terrific talk. Thank you very much. And this concludes today's talk.